Hello everyone. In the heat transfer lecture series, in previous lectures we have seen the heat transfer through a plane wall and composite wall and how to solve the problem based on this concept. Now in this lecture we are going to study about the heat conduction in cylinders and the spheres. Okay. So in that, here temperature is temperature in the cylinders is depend upon the temperature is based on the radius of the cylinder or the sphere. So temperature is the function of radius in the steady and the one dimensional heat transfer. Okay. So in that, if you consider steady heat transfer, so Q conduction in the cylinder will consider as a constant. This is similar for a sphere also. So Q conduction for sphere is also constant. Okay. So here we have considered the cylinder here which has length is L and internal radius is R. So temperature is varying according to the radius. Okay. Now we'll apply the Fourier law of heat conduction for this cylinder. First we will solve for the cylinder. In that in that we have considered the figure here. So there are the two we will consider the hollow cylinder, that means a pipe section. There is in internal radius we have, there is R1 and outer radius is R2. Okay. So R1 is internal radius and R2 is outer radius. So temperature at inside is T1 and outside of the cylinder is T2, and thermal conductivity of material used for this cylinder is denoted by the K. Now applying the Fourier law of heat conduction, applying Fourier law of heat conduction So we'll apply, this is for the cylinder first. This is equal to K minus Ka dt by dr. Okay. So here now here we will consider, obviously heat transfer is available to the surface of the cylinder. So here A is 2 pi r into L. Okay. If you substitute the value and if you solve, this is for a limit temperature changing between T1 to T2 when radius will be changing from R1 to R2. Okay. So according to this limit we will solve this equation. So for that we have considered, so we will consider here Q dot divided by Q dot conduction for cylinder divided by area multiply with the dr is equal to minus K into dt. Okay. Now now for this equation we will consider a limits to solve this integration with the limits R1 to R2 Q dot conduction of cylinder divided by area of cylinder multiply with dr is equal to integration minus integration T1 to T2 K into dt. Okay. If you substitute the value of A as A is equal to 2 pi r into L, then we will get, after solving this equation, we will get Q of conduction of cylinder is equal to 2 pi L K multiply with T1 minus T2 divided by ln R2 divided by R1. So this is the formula to find out the heat transfer through the cylinder when cylinder has inner radius and outer radius and only one layer which is consist of the thermal conductivity as K. Okay, now if you convert this formula into a thermal resistance, just like Q is equal to delta T divided by resistance. If you compare these two formulas, you will get resistance of the cylinder. Resistance for the cylinder is equal to ln R2 divided by R1 divided by 2 pi L into K. So this is the resistance offered by a cylinder for the conduction heat transfer through that cylinder. Okay, now now similarly we will see for the spheres also, for sphere, and for the sphere again we'll consider a same Fourier law of heat conduction equation, Q conduction for sphere. Okay, so this is equal to, again we will consider minus K A dt divided by dr. So figure for the sphere is also same. Consider, if you consider figure for the sphere is same, if you consider this figure as a sphere figure, there is internal radius and outer radius. Thermal conductivity of material is K, internal temperature is T1 and outer temperature is T2. Okay, so based on this, so we will again change this equation as similar as R1 to R2, Q of conduction of sphere divided by area of sphere multiply with dr is equal to minus K integration temperature changing from T1 to T2 into dt. Okay, so here surface area of sphere is equal to 4 pi r square. If you substitute this value in this equation, we will find out Q of conduction of a sphere is equal to 4 pi r1 r2 into K multiply with T1 minus T2 divided by R2 minus R1. Okay, now to find out the resistance offered by a sphere, so resistance offered by a sphere material with internal radius is R1 and outer radius is R2. So thermal resistance offered by a sphere, this is equal to R2 minus R1 divided by 4 pi R1 multiply with R2 multiply with K as a thermal conductivity. Okay, so this formula is used to find out the heat transfer through the sphere, and this is a resistance offered by a sphere material to the conduction heat transfer. Okay, now here we will consider a steady heat transfer through the cylinder. In that we have considered a cross-sectional area of the cylinder. Inside temperature of the cylinder we have taken as T infinity 1, that means one of the fluid is flowing through the pipe, and outside there is a surrounding temperature, or the outside surrounding fluid is flowing over this cylinder. Okay, inside surface temperature of cylinder is T1 and outside surface temperature of cylinder is T2. Internal radius is R1, outer radius is R2. Thermal conductivity of this material, if we consider as K, there is, if one of the fluid flowing through the inside of the cylinder, we have the heat transfer coefficient as H1 as inside, and the surrounding fluid flowing over the cylinder, that means heat transfer coefficient outside of the cylinder as H2. Okay, so for that, if you draw a thermal network, we have the three resistances here. The first one, the first resistance is heat transfer by the convection inside of the fluid. So temperature, higher temperature will be reduced from T infinity 1 to T1. Okay, then into the cylinder material, heat transfer is by conduction, that means resistance offered by this material, it is by the resistance due to the conduction heat transfer. And the next one, if the surrounding fluid flowing over this cylinder, that means there is convection heat transfer, that means there is a heat resistance is offered by the surrounding material to transfer the heat, and this is by thermal resistance by the convection. So that means there are the three resistances. Okay, now so we can use a formula. Q is equal to delta T divided by R total. So here T1 minus T2 divided by total thermal resistances. And if you see in the figure, these resistances are available in series. So we can find out R total is equal to, so this is first resistance is R1, second is R2, and third is R3. So R1, that means R1 is, it is by the convection 1, plus R2, it is by conduction into the pipe material, plus the resistance at the outside of the material, outside of the pipe or the cylinder, this is R convection 2. Okay, so this is also R1 plus R2 plus R3. Okay, so here we will find out this is equal to, if there is heat transfer by the convection, so we have the formula is 1 upon A1H1 plus, it is heat transfer by conduction, so we will consider it is ln R3 by R2 divided by 2 pi L into K, plus outside heat, outside thermal resistance by the convection, this is 1 upon A3 or A2 H2. Okay, so A1 we have considered, A1 is equal to inside area is, inside surface is 2 pi R1 into L, and A2 is 2 pi R2 into L. So for that, R total is equal to 1 upon 2 pi R1L H1 plus ln R2 by R1 divided by 2 pi L into K, plus 1 upon here 2 pi R2 L into H2. So this is the thermal resistance in this figure. If you substitute all this in this formula, we will get it the total heat transfer from this cylinder. Okay. Similarly, if you solve same for this sphere, this is for sphere. So R total. So figure thermal network for this sphere is also same. Okay. So R1, R2 and R3, these are again same, the resistances available in series, and from that we will see R1 plus R2 plus R3. So here R1 is by convection heat transfer, R convection 1 plus R conduction plus R convection 2. Okay, so here again same 1 upon A1H1 plus, so R conduction R1 minus R2 divided by 4 pi R1 R2 into K plus 1 upon A2H2. This is equal to, so we know that surface area for this sphere A1 is equal to 4 pi R1 square. Okay, and A2 is equal to 4 pi R2 square. Okay, we'll substitute in the formula the total thermal resistance into the sphere. So here we write down the sphere as 1 upon 4 pi R1 square into H1 plus R2 minus R1 divided by 4 pi R1 R2 into K plus 1 upon 4 pi R2 square into H2. Okay, so this is, we consider a convection heat transfer of inside of the sphere and convection heat transfer outside the sphere. Then total heat transfer we will find out by using this one. We substitute this value in heat transfer formula, we will get the answer. Okay. Now we'll see multi-layer cylinders and spheres. So in this figure we have considered a cylinder which has 3 layers of the material. So material, if you consider as the first material, thermal conductivity is K1, second material thermal conductivity is K2, and third material as thermal conductivity K2. If you consider the radius as inner radius is R1, then R2 radius is outer radius of the material, first material, then R3 is outer radius of second material, and R4 is outer radius of third material. Okay, so here if again you will consider there is a fluid flow inside of the cylinder and which has a temperature T infinity 1 and heat transfer coefficient is H1. So that means there is a heat transfer by convection from the fluid to the cylinder wall. Okay, the first inside surface temperature of the first layer as T1, outside of that one is T2. Then second material outside temperature is T3, or we can say at the interface of the second and third material temperature is T3 and outside surface temperature of the cylinder as T4, and surrounding temperature of the fluid is T infinity 2, and there is heat transfer by the convection, that means heat transfer coefficient is we are taken as H2. Okay, now we'll draw the thermal network. So here thermal network, so first there is heat transfer by the convection, that means there is a convection resistance as R convection 1 from temperature T infinity 1 to T1. Then from T1 to T2 there is a solid material is available, so that's why the resistance offered by, or the heat transfer is by conduction, and there is a R conduction 1. Then second material similar one, there is a heat transfer by conduction. Okay, that means R conduction 2. And I think again similarly third material there is a resistance offered by this material is R conduction 3, and outside there is heat transfer by the convection, that's why the resistance is offered as R convection 2. So temperature T infinity 1 to T1 the first resistance, T1 to T2 second resistance, T2 to T3 third resistance, T3 to T4 this R conduction third resistance, and the temperature T1 to T4 to T infinity 2 their resistance is R convection 2. Okay, if you see all these resistances are available in series, so we have the formula is Q is equal to t infinity 1 minus t infinity 2 divided by r total. Okay, if you consider this is a cylinder, then we have the r total, we can find out as 1 upon a1 h1 plus, now this is conduction, that means ln r2 minus r1 divided by 2 pi l into k. So length of the cylinder is same one, plus r conduction 2 ln r3 minus r2, sorry, this is not minus, this is divided by 2 pi l k2 plus ln r4 divided by r3 divided by 2 pi l into k3 plus 1 upon, we'll consider this is fourth radius a4 into, why this fourth radius, because radius fourth area we will consider the radius is r4, so a4 into h2. Okay, now we will solve this. R total is equal to 1 upon 2 pi r1 l into k1 plus ln r2 by r1 divided by 2 pi l k1 plus ln r3 by r2 2 pi l k2 plus ln r4 by r3 divided by 2 pi l k3 plus 1 upon 2 pi r4 l into, sorry, this is not k1, this is h1 and this is h2. Okay, so this is for a multi-layer cylinder, if you consider the 3 layers of the cylinder material. Okay, similarly, if you consider this is a sphere, if you consider this is a sphere, that means material 1, material 2 and material 3 are the layers of the sphere. So in that we have again same, we can find out for spheres r total is equal to 1 upon, so r total is again as r convection 1 plus r conduction 1 plus r conduction 2 plus r conduction 3 plus r convection 2, same as before. Okay, now r total is equal to 1 upon a1 h1 plus 1 upon a1 h1 and the conduction resistance as r2 minus r1 divided by 4 pi r1 into r2 into k1 plus r3 minus r2 divided by 4 pi r2 into r3 into k2 plus r4 minus r3 divided by 4 pi R3 into R4 multiply with K3 plus convection heat transfer 1 upon A4 into H2. So here A1 is equal to 4 pi R1 square and A4 is equal to 4 pi R4 square. If you substitute the value in this formula, we will find out the heat transfer or the total thermal resistance for a sphere, which consists of a 3 layers, and inside there is a convection heat transfer, and again outside is again there is a conduction heat transfer. Okay, so this is the formula for total thermal resistance. This formula, according to this formula, we will substitute Q is equal to T infinity 1 minus T infinity 2 divided by R total. In that formula, if you substitute the value of R total, then we will find out total heat transfer. Thank you.